Today we'll be doing the last tutorial covering softwares to do uncertainty analysis with. Today we'll be using MatLab. So you go ahead and open your MatLab. We're going to use the strain gauge lab as the means to show as an example of how you can use MatLab to do uncertainty analysis. Once MATLAB's finished opening, you'll get this following window, and it'll tell you where the current folder is. Now we need to change that current folder to where we have our text file that we have used for import, and in this tutorial it's on the desktop, and now you can see all the icons on the desktop on the left here under the viewing, and this is the data that we want to import. This import file was used in the MathCAD uncertainty tutorial part, so if you look at the first 5 minutes of the MathCAD uncertainty tutorial, it'll show you how to create this input file. Now what we're going to do is we're going to start a new file. So you're going to hit the new button on the top left there. Now this is the command window. This is where it will display messages and display calculations if you tell it to. So the first thing you do in MATLAB is we need to make comments, and to make comments you do a %, and we're going to say starting off with a clean slate. So what we're going to type in now is CLC, which means it clears out the memory, and then you're going to type in clear all and then close all. This way, if you have any figures open from previous runs, it will close them and get rid of them. So now the next thing we need to do is we need to import the data that we have. So importing the data from the text file. So I'm going to import it to the variable A, and I'm going to say it's equal to DLM read, and then now I'm just going to say the file name, lab4 data.txt. So now that we got the data imported, we need to define the data in that into single vectors so that we can read it. So now we're going to say defining the variables ls, m, strain, and Young's modulus. So I'm going to say ls is equal to a of the first whole, we're going to do the first row, first column of A. Now, to see if this is importing correctly, we can hit run, and then it'll show you if there's any errors, and they're showing there is an error. And I believe the index starts at 1, and that was the problem. And you can see that it imported the ls properly. So now if I put this colon back and I hit run, you notice it doesn't show anything, it suppresses it, which is what we want it to do. So it doesn't display that value. Next is m, and that's equal to a of colon. What this colon means is that it takes all rows, and then you only want the second column. And now I want to import e. I'm going to make a little e strain. And then finally Young's modulus, big E. And now we've imported all that data. So now we need to define the parameters of the uncertainty as well as parameters of the bar itself. So defining the beam dimensions and uncertainty. So my base was equal to 25 millimeters or 0.025. My height was equal to 10 millimeters or 0.01. And then u of the base was, I'm just going to put a hypothetical value in of 0.1. And u of the height is equal to u of the base. Now uls, I'm going to say is 0.1 as well. u of m, I'm going to say is 0.5. Now each of these are in their base units. So this is in kilograms, this is in millimeters, this is meters, this is meters, and this is meters. So keep in mind you put everything in here in base units. And if you want to remind yourself, you can put a comment to it in meters. Here we can say it's in meters. In meters. That way we know the units. In meters. So now that we inserted that, I'm going to actually separate this. I'm going to say defining the uncertainty values needed for Young's modulus. And now I'm going to define the uncertainty values for the DAQ itself. So the first thing we need to insert is VEX, which was 5 volts. So this is in volts. And then the next thing we need, I'm going to make that capital. We need VI, which I said is 1.6 millivolts from before. So 1.6 times 10 to the minus 3. And that's in volts. And then we need the gauge factor, 2.05. And then we're going to say, instead of uncertainty values, defining the necessary values for calculating the uncertainty of the DAQ. And then the next thing we need to do is calculate V0. So we're going to calculate V0 using the equation before. So we're going to say, well, the bits is equal to 24. Range is equal to 25 times 5 minus a negative 5 times 25. And that's in millivolts, so I'm going to go ahead and multiply that whole thing by 10 to the minus 1, or minus 3. And then the resolution is equal to range divided by 2 to the bits minus 1. So then, now calculating V0. So V0 is equal to VEX times gauge factor times E, and since this is a matrix, you got to do the matrix multiply, which is the period E, and then we need to put parentheses around this, divided by 4 plus VI. The matrix is the dot matrix multiplication is supposed to be in front of the multiplication sign. So now if I hit run, you see it calculated V0 for me. So again, when you do a multiply in MATLAB and you put a dot in front of it, it means a matrix multiply, which means that it takes each individual parts of that matrix and multiplies it through and then gives you a matrix output. So now we know V0 is calculated, right? I'm going to go ahead and suppress it on output. So now we can start calculating the DAQ uncertainty. So now calculating the uncertainty of the DAQ. So U0 is equal to res divided by 2. Now UCZE, the 0 uncertainty, is equal to 0.05 divided by 100 times the range. And then UCSEVI is equal to 0.02 divided by 100 times V dot I, or VI. And then UCSEV0 is equal to 0.02 divided by 100 dot times V0. And if we hit run now, it should give us the values of V0. And you can see it does. And you can see it's times 10 to the minus 6. Now I'm going to suppress that. And now we're going to calculate UC of VI, which is equal to UCVI is equal to square root of UCZE squared plus UCSEVI squared. And now when I hit run again, I should see a value for it, which I do. So I'm going to suppress it now. So I'm going to say now calculating the UC, the overall UC uncertainty. Now UCV0 is equal to the square root of UCZE squared plus UCSEV0 dot squared. And the reason why we have to do that dot is because it's a matrix again. So you put a dot in front of it to let it do matrix calculations, and you can see it did that. I believe it's supposed to be 0.2 here. So there's a small error. So make sure you put in the proper value for the sensitivity error. And then now we're going to calculate the actual UD, or overall uncertainty for the DAQ. So UD VI is equal to the square root of U0 to the second plus UCVI to the second. Then we'll suppress that as well, and then UDV0 is equal to the square root of U0 to the second plus UCV0 dot squared, because it's a matrix. And now we've calculated the uncertainty of the DAQ using MatLab. Now the next part we're going to do is calculate the uncertainty of strain. So now calculating the uncertainty of strain. And we're going to do that as UE is equal to E dot times square root of the uncertainty of VI divided by VI. And we're going to square that, plus the gauge factor and its uncertainty. We haven't defined the uncertainty of gauge factor, so I'm going to go ahead and define it before U0 here. So UGF, I'm going to say, is 0.1. So plus UGF divided by GF squared plus, now we got to do the uncertainty of UDV0. And the way we're going to do that is UDV0 dot divided by V0 dot squared. And now when we hit run, we should get our results. And there's no function VI defined, so I forgot to put capital V here. So remember that the scripts all matter. And you can see here it calculated the uncertainty of strain. And now the last thing we need to calculate is the uncertainty of Young's modulus. So now calculating the uncertainty of Young's modulus. We're going to say U big E is equal to big E dot times squared of square root of U of base, so U base divided by the base squared plus 2 times U of height divided by the height squared plus U of mass dot divided by mass dot squared, because it's a matrix, and then ULS divided by LS dot squared plus UE dot divided by E dot squared. And make sure that your parentheses line up, and then if we hit run, and make sure that all your matrices all line up. Forgot to put a capital LS here because it wasn't showing referencing the right variable. So now if we hit run, it should work, and you can see that we have our uncertainty for Young's modulus. Now the last thing we can do is we can export all the uncertainty values like we did with MathCAD, and we're going to say now exporting the results of uncertainty. We're going to say data is our vector we're going to define, and we're going to say that all the rows is going to be the first column, and the first column we're going to have is V0. And then the next thing we want is the uncertainty of VI. So I'm going to say 1, 2 is equal to VI. Then the next one I want is all rows, third column equal to U dV0. Well, and the second, we should make the third column equal to U dVi, and then the fourth column is the uncertainty due to V0. Then the fifth column is UE, and the sixth column is going to be uncertainty of Young's modulus. And now if we just print out that matrix that we're creating, we should be able to see that all of it comes together. And you can see that. And then now we actually need to write that file. And to write that file, we're going to just say, and we're going to add one more parameter after this. So you type in delim-write uncertainty results.txt, and we're going to say it's data. Then we're going to say tab. So that way it's a tab delimited file when we hit it. So we hit run now, and then we should see a new file, and it's going to be a tab delimited file. I'll go ahead and open it in Excel. File, open. And then you notice, ta-da, you have your matrix. You know this first one's your V0s. You know this is VI. This is VI uncertainty with UDVI. This is UDV0. This is the uncertainty of strain. This is the uncertainty of Young's modulus. So we have successfully written a MATLAB code to read our results, then to define those results in matrix we imported, define the beam parameters, define the uncertainty of the beam parameters, define the DAC parameters, define the uncertainty of the DAC parameters, calculate V0 based on the matrix of strain, then how to do uncertainty analysis using a matrix and the dot with the power to signify a multiplication of each individual components in that matrix, then compile the matrix to write to a file so you can save the outputs and show them in Excel. So this is how you use MATLAB as a tool to do uncertainty analysis. And I'm just going to save the M file as lab4 uncertainty. And you can go from there. And then when you're done, you just close out of MATLAB, and that's all you need.